All right, calculus. I am starting to move into chapter 7 and chapter 8. Now I combine them both because we only do bits and pieces of both chapters because you've already done some of this stuff before. So I actually skip the sections that we did before and I go straight into the more calculus part of it. In other words, the things that have to do with derivatives and stuff. It's at this point in the course where I sort of feel like you've learned the basics. You've learned your basic rules for derivatives. You've learned the product rule, the quotient rule, the chain rule. You've learned implicit differentiation. And then in the last chapter, you learned how to curve sketch, find areas of increase, decrease, local max, local mins. I feel like now what they do is they start taking those things into more complex questions, into things that are a little bit more complicated to deal with than what you've seen before. So it's taking what you already know and applying it to more complex situations and more complex types of questions. I'm going to take you slowly through this, so don't worry too much. Like I said before, we're going to skip parts of it because you've already done it. So, and so that's why I kind of put it together. Chapter 7 deals with exponents and logs. Now, we've already dealt with exponents and logs, logarithmic rules, all of those things. We've already dealt with them. So they actually spend the first 5 sections just doing what we already did in chapter 2 of grade 12 math. So there's no sense in redoing it. You just did it in like October of this year. So there's no point in redoing it. So we're actually going to jump ahead and we're going to jump all the way to section 7.6. Now, I am going to be reminding you of things as we go through this. So if you're like, I don't remember any of that, don't worry, okay? I'm going to talk you through it. But there's no sense in spending weeks, because we don't even have weeks left, but there would be no point in spending weeks reviewing something that in theory you should already know. So, section 7.6 talks about derivatives of exponential functions. So far, when we have done a derivative, for example, it would be something like 6x cubed. The exponent would be a number, okay? And so you would just bring the 3 down in front, decrease it by 1, and you get 18x squared. But what happens if the x is actually in the exponent? So you have like, I don't know, 16 to the 4x squared. So that is actually your exponent. What do we do then? How do we do a derivative with that? Because I can't just subtract 1 from 4x squared. So that's where we're headed with this, all right? We're going to build up to it slowly, but that's where we're headed with that. Okay. One of the things that we learned in grade 12 was that when we deal with something that is continuous growth or continuous decay, so it doesn't like grow for 2 weeks, but it grows exponentially forever. We dealt with a growth constant E, and that's a button on your calculator. It's 2.718 and it keeps on going. And we said that if you are doing a logarithm where the base is E, that's actually something called a natural logarithm. We call it LN, logarithm naturel, for short. And so log of base E is really your ln button on your calculator. So that's going to come into play in this section. All right. Most of the time, when we deal with an unknown in an exponent, a lot of times the base e will be there. So on page 451, and they spend some time explaining this from page 449, 450. They spend a lot of time explaining this. I'm going to ask you to trust me. If you don't and you want to read about why that is, you can read page 449 and 450. But they explain to you why this is. If you are trying to take the derivative of e to the x, if you are trying to take the derivative of e to the x, turns out the derivative is e to the x. It doesn't actually change, okay? The derivative of e to the x is e to the x, all right? It just, and again, they explain it all on page 449 and 450. What happens when I explain it, though, is people go, I don't get it. Don't worry about it. Just trust me, okay? The derivative of e to the x is e to the x. And so in example 1 on page 451, they talk about limits, okay? If I were to graph y is equal to e to the x, that's an exponential graph. We talked in grade 12 about graphing something like y is equal to 2 to the x. And if you do a table of values, okay, if you do a table of values, no matter what the base is, if your x is 0, in other words, your exponent is 0, it doesn't matter what your base is. 2 to the 0 is 1. E to the 0, also 1. 1 million to the 0, also 1. So it doesn't really matter what your base is. If your x is 0 and your x is the exponent, your y value is automatically 1. Now, if you're trying to graph e to the x, and again, if you did a table of values with this, if you did e to the first, then it would be 2.718. So it'd be up here somewhere. If you do e squared, well, it would be 5 point something. It would go up. If you did e to the negative 1, it would end up being less than 1. It would start being a decimal. What you would find if you did a table of values is that your graph would look like this. Any exponential graph looks like this. The bigger the base, so this base is 2.718 because that's e. If my base was 10, then this line would go up faster and down faster. But it would remain that it stays above the x-axis and it goes up this way and down this way. So now if we start talking about limits, what is my limit as x approaches infinity for e to the x? So think about what that's asking you. If my x was infinity, if it was a really big number, if I had e to the thousandth, okay, if I had e to the 1,000, that's a really huge number. That's really high up there. So what is my limit as x approaches infinity? Well, it's infinity because the answer is extremely large. It's very, very big. Now, what is my limit as x approaches negative infinity for e to the x? So this time, instead of putting e to the 1,000 in my calculator, I put e to the negative 1,000. Well, notice as my x value gets lower and lower, my graph gets closer and closer and closer to 0. So my limit as x approaches negative infinity is 0. Okay. That's not a big deal. Don't worry about that too much. Now, what they have found is there is a way, so the derivative of e to the x is just e to the x. But what if it isn't just x as my exponent? What if it's something else? There is a way to do this. And again, we could prove it by doing derivative by first principles, but that's going to suck. So I'm going to go straight to the shortcut. So there is a way to do this. And if you want to find the derivative of e to the something, okay? The derivative, so if you want to find the derivative, and they write it this way, if you want to find the derivative of e to the g at x, so e to the something, then first you do the derivative of e, which is just e. Leave the exponent alone. Then you do the derivative of the exponent. Okay. So if you want to find the derivative of e to the g at x, this is what I would call almost a modified chain rule, because it's sort of like the chain rule where you do the outside then the inside. It's sort of like that. First I do the derivative of e, which is just e, and I leave the exponent alone. Then I do the derivative of the exponent. So let me show you what I mean. Example 2, there's an a and a b. I'm actually going to do b first. Now they explain it differently than I do. I don't like how they explain it. To me it's very confusing. So I'm going to explain it my way. 2b, they want you to find the derivative of e to the 7x. So if I'm going to find the derivative of that, I'm going to use this rule, okay? I'm going to use this rule. First, you find the derivative of e, which is just e. And you leave the exponent alone. Once you've done that, then you find the derivative of whatever's up here. So what is the derivative of 7x? It's just 7. Now this is written kind of awkwardly, so I would write this 7e to the 7x. That is the derivative. Don't overcomplicate that. Don't overcomplicate that. It's not that bad, okay? Don't overcomplicate that. So they do that one second. I did it first, because the one that they do first, A, I find is more complicated than that one. So we're going to look at example 2a, which is y is equal to x cubed e to the x. So if I'm going to find the derivative of that, first off, I'm multiplying two things. I'm multiplying this with this, okay? So I'm multiplying these two things. So this would be f, this would be g. So I have to do the product rule here. So that is g f prime plus f g prime. So if I do the derivative of this, I leave g alone, which is e to the x, and I do the derivative of f. Well, the derivative of x cubed is 3x squared plus. So here is my g, here is my f prime. Plus, now I'm going to leave f alone, so that's x cubed. But now I have to do the derivative of g. I have to do the derivative of e to the x. So again, following that rule, first I do the derivative of e, which is just e, leave the exponent alone. Then I do the derivative of x. I do the derivative of the exponent. The derivative of x is just 1. So I'm going to clean this up just a little bit. Y prime is equal to 3x squared e to the x plus x cubed e to the x. No need to put the 1. Now, they leave it like that in the textbook, in this case. But sometimes they like to simplify it. And I have come up against professors who would be very angry if I left it like this. Because technically speaking, I could take a common factor out of here. There's at least an x squared in both pieces, and there is an e to the x in both pieces. If I take an x squared and an e to the x out of here, I have 3 left. And if I take an x squared and an e to the x out, I have an x left. This way is fine. This way is fine. What I will tell you is if you are going on next year into another calculus class, your professor could be picky enough that this is not okay with them. They want it like this. I don't care. Professor might care, all right? Okay, I'm gonna do one more example and that's all I'm doing today. One more example and that's it, I'm done for today. So, think back, way back to October, when we did word problems with exponents and we talked about exponential growth. And if it had an E in it, if it was continuous growth, it looked something like this. And I'll use A's instead of P's, it doesn't really matter, but the final amount, the amount you end up with is equal to the original amount, E to the K times T. If it is continuous growth, not we're gonna watch it grow for a day, but it's a continuous thing. It is E to the K times T. K is a growth constant, so it grows 14% per day. Your growth constant would be 0.14. And T is the time for which your experiment goes, okay? So, we are going to look at example 3, and I'm going to bring in something else that's new in this. It's easier to explain as I go. So, in example 3, it says you have a tuna fish sandwich. This is gross. You have a tuna fish sandwich. Number 1, ew, but anyway. And you leave it out of the fridge. You set it on the counter and you forget about it. Ugh. All right? The bacteria on that sandwich is going to grow exponentially. So to begin with, everything has bacteria on it all the time. So to begin with, it already had 600 bacteria initially. So my AO is 600. Okay? Now, and time is going to be measured in minutes. They tell us that. So when we do T, we're going to put it in minutes if they don't already. The growth constant K is 0.012. So my K is 0.012. And the amount of bacteria that I have left will depend on the time that I leave it sitting out on the counter. All right? So part A just says determine an exponential equation. We just did that. That's part A. They just wanted you to set it up. So I just set it up. Okay? Now, the question that they ask now is when, so we're looking for a time, when will there be 1,800 bacteria in the sandwich? All right? Eventually, we are going to start dealing with having to do the derivative of a question like that. If we had to do the derivative of a question like that, the rate of change would be in there somewhere. What is the rate of change of? Would be in there somewhere. The words rate of change are not in here anywhere, so that means we don't have to do the derivative for this one. So there's not a whole lot new in here, except that I want to jog your memory on how to do a question like this. All right? So when will there be, so I'm looking for time, 1,800 bacteria on that sandwich? So when will the amount of bacteria be 1,800? So basically, how long will it take it to triple in the amount of bacteria it has? Remember, time is in minutes. This is going to gross you up. So A is going to be 1800. That's equal to 600 e to the 0.012 times t. So I'm trying to figure out t. So I'm going to divide this side by 600. So I'm going to divide this side by 600. So that's going to be 3 is equal to e to the 0.012 t. Here's where we review stuff we did back in October. If my unknown is up here, what do I do in order to solve a question like this? Well, this is a pretty simple question. There's no pluses or minuses. It's an answer, and it's an e to the 0.012t. I am going to change this into logarithmic form. I'm going to change this into logarithmic form. So remember, whatever the base in my exponent is, that becomes the base of my log. So it's log base e. Whatever my answer is in exponential form, that's what I'm taking the log of. Whatever my exponent was, that is now my answer. So I've gotten rid of the exponent because I can't solve when there is an unknown in an exponent. Now, log base e. Back a little while ago at the beginning of this video, I said, remember, if you have log with a base e, that is a natural logarithm. That is ln. You have a ln button on your calculator. You can actually put ln 3 in your calculator and get an answer. Now, I'm trying to figure out time, so I'm going to divide this by 0.012. So I'm going to divide this by 0.012. And so in my calculator, I'm going to put ln of 3. I would hit equals just to get the answer. And then I would put divided by 0.012. You get 91.6 minutes. It only takes an hour and a half of your sandwich sitting on the counter for your bacteria to triple. It's kind of gross. All right. That's it. That's all we're doing for today. We are going to finish up section 7.6 on Thursday. Again, we're only doing certain sections, so just to give you an idea of where we're headed, we're going to do section 7.7. We're going to do section 7.8. And then we jump all the way to section 8.3. And we do section 8.3 and section 8.4. And that's it. We're done. In section 8.4, at the very end, there are some questions that are going to challenge you, because they're going to take literally everything that we have learned in this whole textbook and put it all together into just a couple of questions. So we will get there. We will break those down slowly. But we don't have a lot left to do, so that's the good news. Next week, even if, we won't be done this early next week, but even so, early next week, I'm going to upload the big long project I want you to do so that you have lots of time to work on it. But I'm hoping to finish this off in time that you have at least a week where all you have to focus on is that assignment and you don't have anything else from me. Okay? So, but I'm going to upload it earlier than that so you can start it whenever you want. Okay? And it'll be due by June 5th. All right. So I think that's it for today. I think I'm done talking. Yay. I'm going to go upload these videos for you. Bye.